Welcome. So let's learn another theorem related to tangents. And this is in your notes. You're going to fill in the red words. Those are the missing words. So tangent segments to a circle from the same external point are congruent. So in the diagram here, we have two tangents. We have tangent AB. So AB is a tangent to circle O at point A. So this is where it intersects the circle. And notice it does not go beyond that point. CB is a tangent to circle O at C. And again, the tangent intersects the circle at point C and does not go beyond that point. And notice that the two tangents, AB and CB, intersect in a point. So tangent segments to a circle from the same external point are congruent. So if you have two tangent segments, meaning they're finite, they don't go beyond the point of tangency, and they intersect at the same point, they're going to be congruent. So since AB is a tangent to circle O at point A, and CB is a tangent to circle O at point C, then AB is congruent to CB. So if you know the measure of one tangent segment, you know the measure of the other tangent segment because they're congruent. You may think of this as the hat theorem, and it's really called that because the diagram looks like a circle wearing a pointed hat. So remember that picture, and you'll remember that these two segments are congruent. So now let's solve some problems. Oh, actually, excuse me, no. First, let's prove that it's true, and then let's solve some problems. All right, so we are given, so I have all the steps here, and they could be written a little neater, I guess, but we have all the steps here, and we're going to justify each of our steps. So we have the statements, and then we're going to come up with the reasons why we can say these things. And our goal is to prove that RA is congruent to TA. Because you shouldn't take my word at it. Let's prove that that's so. Just because I said so, that's not enough. Let's prove it to be true. So we're given some information. We're given circle P. You need to have a circle to start with. And we're given that PT and PR are radii of circle P. And that's marked on the diagram. RA and TA are tangents of circle P, and we want to prove RA is congruent to TA. Right, so this is our initial diagram, and actually this is not in the initial diagram. That's our initial diagram. Two radii and two tangents. All right, so our first step is PT and PR are radii, and RA and TA are tangents of circle P. And by the way, this should have the correct symbol, so let's fix that. So how do we know that PT and PR are radii? And how do we know that RA and TA are tangents? Well, we were told that. That's our given information. We need to have a circle, we need to have radii and tangents if we want to prove something about those tangents. So that is given information. You always have to have a starting point. Line PA. Well, anytime I have a line, I am free, anytime I have 2 points, I am free to connect those with a line. So we have connected the 2 points with a line, creating segment PA. So why do we have line PA there? Well, it's because any 2 points can be connected by a line. And that was something we learned at the very beginning of the year. And that line is going to be important to us. And actually, we're just dealing with the line segment because it's going to stop at P and A. We don't care about anything beyond that. So PA is congruent to PA is congruent to PA. All right, well, how do we know that segment is congruent to itself? That's the reflexive property. And if you notice here, together the two radii and the two tangents and that line PA that we've drawn create two triangles. So maybe we're going to do something with congruent triangles to be able to prove the tangents are congruent. And if you were thinking that, you're exactly right. Right? Because we have congruent shortcuts for triangles, and we know that if we can prove the triangle's congruent, then we know all of the corresponding parts are congruent. So here is a connection to working with congruent triangles and using that to actually prove that our tangents are also congruent. PR is congruent to PT. Well, how do I know that PR is congruent to PT? Well, we said that they were radii of a circle, and we know that all radii of a circle are congruent. Angle R and angle T are right triangles. Excuse me, are right angles. So I'm now saying that these are right angles. How do we know they're right angles? Right? Well, in the last lesson, we learned about the properties of tangents. And we learned one of the key properties is that tangents are perpendicular to a radii at the point of tangency. R and T are the point of tangency because that's where the tangents intersect the circle. PR and PT are radii, so therefore, since tangents are perpendicular to radii, that has to be a right angle. So angle R and angle T are right angles because tangents are perpendicular to radii at the point of tangency. That is always true. That's a defining feature of a tangent. Triangle RPA and triangle TPA are right triangles. How do I know that's a right triangle? Well, what do we know about a right triangle? We know right triangles have one right angle. So right triangles contain a right angle. If a triangle has a right angle, it's got to be a right triangle. Oh, let's see if I can just squeeze in the angle, the symbol there. There we go. Step 7, triangle RPA. So now that I know they're right triangles, I now have enough information to say triangle RPA is congruent to triangle TPA. If you notice, this side here is the hypotenuse of the two of each of the right triangles. Right? Hypotenuse is opposite the right angle, and this is a leg. The two radii are legs of the right triangle. Right? So if you know you have a right triangle and you know if you know you have two right triangles and you know you have a pair of congruent legs and a pair of congruent hypotenuses, if you know the hypotenuse in the two triangles is congruent, then you know that the triangles have to be congruent using hypotenuse leg, triangle congruence theorem. And by the way, to use that theorem, you do have to state that the triangles are right triangles because you can only use that theorem in right triangles. And now that we know that RA has to be congruent to TA. And how do we know that? Because corresponding parts of congruent triangles are congruent. And sometimes that's abbreviated CPCTC. Right? So if you see CPCTC, it stands for corresponding parts of congruent triangles are congruent. We used a shortcut to prove the triangle is congruent, but if the triangles are congruent, it means that all 6 corresponding parts are congruent, not just the 3 that we used. Now that we know for sure that tangents that intersect in a point, tangent segments, that intersect at a point are always congruent, now we can solve some problems because we have proved it to be true. And some of these are in your notes. I believe this one is. If I move over, yes, this one is. All right, so we're given RS is a tangent to circle C at S, and RT is tangent to circle C at T, and we want to find X. We have two tangents that intersect at a point. And how do we know that they're tangents? Well, we're told. That's a given piece of information. Right? We need to either be given that those are tangents, or on the diagram it has to be given that those segments are perpendicular to a radii. Either one would be enough to know that they were tangents. So if they're two tangents that intersect in a point, they have to be congruent. Therefore, 3x plus 4 equals 28. Subtract 4 from both sides. So we have 3x equals 24, and then divide both sides by 3. X is equal to 8. And there we go. You have solved the first one. And then solve another one. As soon as the page turn changes. All right, AB and CB are tangents. We want to find X. So the second one's in your notes, not the first one. Again, if we have tangents that intersect at a point, they are congruent to one another. So we know that 7x plus 5 equals 16x minus 22. Let's subtract 7x from both sides. So we have 5 equals 9x minus 22. Add 22 to both sides to get x by itself. We have 27 equals 9x. And the last thing is we need to isolate the x by dividing both sides by 9. 27 divided by 9 is 3. And that is the value of x. And if you wanted to check that you were correct, you can always plug it back in. So what if, for instance, it said, what's the length of the tangent segments? All right, so then once we solved for x, then we would plug them back in, right, and we would get the measurement. And they should both be exactly the same. So let's check. 16 times 3 minus 22. 16 times 3 is 48. Minus 22 is going to be 26. All right, let's check that out by plugging it into the other expression. So we have, oops, let me write it below rather than above. So we have 7 times 3, because that's the value we got for x, plus 5. That would be 21 plus 5, and that is indeed 26. So you can see that they are both the exact same measurement, and x equals 3 is the correct answer. Let's do the next one. All right, so we have tangents that intersect in a point. They have to be congruent. So x squared minus 4 equals 45. Add 4 to both sides. We have x squared equals 49. Now, x is not exactly a measurement, right? It is an expression that's used to find a measurement, but it's actually not the actual measure of that segment. So when we solve for x squared, we do need to take the positive and the negative square root. The only time we won't is if what we're solving for is just a measurement. Like if we're solving for missing side using Pythagorean theorem, right? Then we won't do that. Right? Then it has to be the positive value. But if we're solving for x, even though x is part of an expression, we do need both the positive and the negative. Now, if the negative makes our segment length negative, then we would throw that answer out. Right? So we're definitely going to check this one to make sure that both these solutions are good. Positive and negative 7 are good. So here we have two solutions, x equals 7 and x equals negative 7. And let's plug them both in and make sure that we get 45 when we plug it back in. Right? So if I plug in positive 7, right, I'd have 7 squared minus 4. 7 squared is 49. 49 minus 4 is equal to 45. Right? So that one checks out. So this is not only our check, it's also, well, we know it's going to be that the measurement of the measure of the segment is 45, right? Because the measure of, oops, we lost a letter there. We know that AC and BC are the exact same length. So if, did I put those letters in the right? Yeah, I guess so. We know that AC and BC are the exact same length. So whatever BC is, AC is the same thing. All right, so now, but we're checking to see if 7 and negative 7 are good solutions. 7 works out. That equals 45. How about if we plug negative 7 in? All right, well, if we're squaring negative 7, that means we're multiplying negative 7 times negative 7, and that is positive 49. So when you square a negative, it is positive. So you see, we have two good solutions. X could be 7, or X could be negative 7. And both are good because they both give you a true statement. All right? So just the second one is in your notes, not the first one. So a little challenge problem there to realize there were two solutions. And I think, I don't know if that's the last one of these problems. I think so. I think I have, oh no, I have two more. These ones are not in your notes. Well, if you get this one as a problem, you better not miss this one, because X is 15. All right, so all you had to remember is that tangents to a segment are congruent. Right? So nothing to solve there, nothing really to solve there. You just had to remember that those two are congruent. Let's solve the last one. Again, we know that AB is congruent to CB. All right, so we set them equal to one another. So we have x squared plus 5 is equal to 21. Subtract 5 from both sides. We get x squared is equal to 16. And now take a square root of both sides. Don't forget positive and negative here. And then we'll check and make sure both solutions work. So we have x equals positive or negative square root of 16 is 4. And let's plug them back in and check to make sure we get a true statement. So let's check the positive 4 first. So 4 squared plus 5, that would be 16 plus 5, which is 21. And negative 4 squared plus 5, that would be 16 plus 5, which is 21. So both of those check out because they both need to be equal to, when we plug them back in, we need to get 21 because that is the measurement of CB. And we know AB is congruent to CB because those are two tangent segments that intersect in a point. The check isn't required so long as you recognize that if you square a positive or square a negative, you're going to get a positive answer. And the only thing is I meant to write in both answers here. I left it as positive and negative 4. Let's instead write x equals 4 and x equals negative 4 as soon as it goes back to the page that I was just on. There we go. X equals 4 and x equals negative 4. And these two are the last of our properties we're going to learn about in terms of segments of circles. That we'll be focusing afterwards on angles and arcs in circles. All right, so theorem 5, if AB is congruent to CD, then arc AB is congruent to arc CD. So in other words, if we have two chords in a circle, and those two chords are those two chords are congruent, the arcs that are created by those chords are also congruent. And I have them marked here, but I'll just outline them again. So in other words, if AB is congruent to CD, right? If those two are congruent, then arc AB, which is the outside portion of the circle there, arc AB has to be congruent to arc CD. That also works the other way. So if the arcs are congruent, if arc AB is congruent to arc CD, then chord AB has to be congruent to chord CD. In other words, in a circle or congruent circles, congruent chords have congruent arcs. And that makes perfect sense, right? If your chords are congruent, you're going to be cutting off that same portion of the circle. And this is all in your notes, and it's already filled in. The last thing we're going to learn about in terms of segments in a circle or congruent circles, congruent arcs have congruent chords, right? So, excuse me, I didn't finish reading the same, sorry, this goes together. I stopped for a second and I didn't finish this second part. So let me just read through that again. This is the last part of Theorem 5, and then we'll look at Theorem 6. By the way, they're only numbered just so that I can list them in your notes. Those numbers don't mean anything. So if we have congruent chords, they have congruent arcs. If the arcs are congruent, then the chords are congruent, right? So you can go either way, right? So if we have a problem and we have the chords marked congruent, just know that those arcs have to be marked congruent as well. So for instance, if this arc here was 52 degrees, then this arc here has to be 52 degrees because the chords are congruent. And now, last but not least, in a circle, parallel chords intercept congruent arcs. Note that the chords aren't necessarily congruent, just the arcs are. So if these two, and this also makes perfect sense, if these two chords are going to be an equal distance apart, well, they're going to cut just as much circle here as they do here, right? So the amount of circle they cut is going to be exactly the same. So if AB is parallel to CD, then arc AC is congruent to arc BD. And the two arcs don't have to be congruent. They could be congruent if they were the equal distance from the center, but they don't have to be congruent. So long as they're parallel, they're going to divide both sides exactly the same. And one last problem. AB is parallel to CD. If the distance around the circle from C to D is 180 degrees, what's the measure of arc CA? Right, so we're given some measurements here. We're told that arc AB here is 80 degrees. And by the way, we're going to be learning why, they didn't have to tell us this, arc CD has to be 180, oops, not very well drawn, but has to be 180 degrees. Notice that segment CD is a diameter. A diameter divides the circle in half. So let's add that. Diameters divide a circle in half. And by the way, I think this problem is in your notes. Let me double check. Yep. So there is some pieces of information already added. I think. Oh no, I'm sorry. I take that back. This problem is not arcs and angles in the next section. So a circle is 360 degrees. If you divide that in half, Half a circle is called a semicircle. You have 360 divided by 2. That would be 180 degrees. So, of course, arc CD has to be 180 degrees. All right, so we were also told in this problem that those two chords are parallel. If those two chords are parallel, that means that, so if CD, cannot write there. Let's write down here. If CD is parallel to AB, then arc CA has to be congruent to arc DB. Right? If these two are parallel, they're going to cut the circle, they're going to cut exactly the same amount from the circle. So if those two are congruent, I could call this one, I don't know either one of them, I could call this one X and I could call this one X. And notice that together, 180 plus X plus 80 plus X equals the whole circle. And a circle is 360 degrees. So let's add our like terms together. 180 plus 80 would be 260. X plus X is 2X. Let's subtract 260 from both sides. That gives us 2X equals 100. Divide that 100 by 2, and X is 50 degrees. And notice that 180 plus 80 plus 50 plus 50 add up to 360 degrees. And there we go. All right, so you can use these theorems to solve for missing segments or missing arcs in circles. In the next series of lessons, we're going to learn how to find the measures of angles and arcs, and that's going to be our most important study when it comes to circles. So thanks for watching, and bye for now.